Hello AP Stat students, Mr. Hazelhurst here again with the second of two videos on the binomial distribution. In the first video we just learned how to apply binomial PDFs and CDFs in different settings, and we learned the characteristics of the binomial distribution. So we're going to use those skills again here in this video. But what we want to begin to look at is how we can use a normal distribution to approximate the values that we would get using a binomial distribution. So again, just a couple of reminders with this video. Pause, rewind as you need to. Make sure you take notes, and be sure to complete the Google form after you finish watching this video. So let's jump right into it. First thing I want to do is show you a couple of different graphs. So what we have here are three different probability histograms representing the number of heads that we would obtain when flipping a coin a certain number of times. So in the graph that we see up here on the top left, you can see that we flipped a coin 10 times, and we've got the number of, or the probability of obtaining a certain number of heads. So you can see we've got a pretty symmetrical distribution here. The probability is of, again, flipping each of these certain number of heads. On this graph, we are basically doing the same thing, but now we flipped the coin 20 times. And finally, this last graph, we flipped the coin 50 times. And so I just want you to think about, what do you notice about these graphs with binomial distributions, these probability histograms representing these different situations? A couple things I hope you notice. Number one, that they're symmetrical. Right? And number two, as we increase the number of trials, what is this beginning to look more and more like? And hopefully what you notice is it's beginning to look like a normal distribution. And again, that's what allows us to apply a normal distribution to approximate these binomial settings. Now again, keep in mind, we're just approximating them. They're not going to be exact. But if we were to take and just draw some normal distributions over these graphs, well, they turn out pretty good. Now we can see that the graph doesn't fit exactly. We've got some areas where the bars extend outside of the normal distribution, and some areas where the bars fall underneath the normal distribution. But as we increase the number of trials, the approximation becomes more and more accurate. Now, this shouldn't really surprise us, because we know from the law of large numbers, as we increase the number of trials, even in probability settings, things tend to center around the true value, and that holds true even in these approximations. So, under what situations can you use the normal distribution? All right, well, first off, we need to realize it's not always going to be a wise idea to approximate a binomial setting with a normal distribution. It's just like a lot of things in statistics. We can do it, it just doesn't mean we should. So the general rule of thumb that we use in statistics is that if our number of trials times the probability of success is greater than or equal to 10, and the number of trials times the complement of the probability of success is greater than or equal to 10, then the normal distribution is going to make an approximate or an accurate approximation. Okay? Now, I'm not going to go through the proofs of why they settled on this number 10, but I just want to show you a website that's got a little applet that we can use to help demonstrate that. So here you can see I have the ability to change my probabilities. All right, so we're going to let the probability of success, we're going to set that to 0.1. And then I have the ability to change the number of trials. And you can see right now that if I only have one trial, whatever this is, if I'm only going to do this thing one time, this would be the probability histogram, the bars that we see here. And you can see a normal distribution fit to the, and you can see that the normal distribution is not very accurate in approximating this binomial distribution. But as I begin to increase my number of trials, here's 5, all right? So if we apply this 5 times, here's the probability distribution. And again, if we continue to increase that, you can see as we increase the number of trials, as n gets larger, and again, we're not changing the probability. The probability is remaining fixed. All we're changing is the number of trials. Well, the larger our trials get, notice that the normal distribution begins to get more accurate. All right? Now, if the rule of thumb is that n times p and n times 1 minus p both have to be greater than or equal to 10, and our p-value is 0.1, what would n have to be in order for this to be an accurate approximation? This normal distribution would be accurate in its approximation of binomial. Well, n would have to be 100, excuse me, because 0.1 times 100 is 10, and 0.9 times 100 is 90, so both rules of thumb would be met. So if we change this all the way up to 100, well, you can see 100 number of trials, you can see this really is pretty accurate in its approximation of the shape of the binomial distribution. Okay? And you can see that changes. If I drop this down to 0.25, right? Well, if it's 0.25, the minimum number of trials that I would need would be a lot smaller. All right? So let's say I go 40. All right? That would be our minimum number of trials necessary. 40 times 0.25 is 10, and 40 times 0.75 is 30. And so again, we can see we're pretty close in our approximation. And it only gets more accurate as we increase the number of trials. Again, that's the law of large numbers at work. So that's what we're looking at here. All right, so let's go back to our slides here. So if we recognize, okay, the normal distribution is going to be accurate in our approximation, what do we need in order to work with the normal distribution? Well, we need to know the mean and the standard deviation. All right? And the good news is, if my setting is binomial, the mean and standard deviation are actually very easy to find. So the formula for the mean of the binomial distribution is just simply n times p. Now, this is a pretty easy formula for us to just logic through. Let me give you an example here. If you were taking a 10-question true-false quiz, and you guessed on every question, on average, how many questions would you expect to get correct? Well, most of you, just using a little logic, would recognize, well, I would expect to get 10 questions on average right. Right? I mean, I have a 50% chance of getting a question, any individual question correct. And that's the same logic that we use in finding the mean of a binomial distribution. We just take the number of trials, 20, times the probability of success, 0.5. And on average, you would expect to get, mathematically, 10 questions correct. All right, so again, you can see this is a very simple formula to set up and use. All right, the standard deviation is also very easy to find. All right, the formula for the standard deviation is just n times p, which is the mean, times the complement of the probability of success. And as always, with the standard deviation, we take the square root. Now, I'm not going to go through the proof of this formula, but you can actually find it in your textbook on page 525, and it's very simple to understand. So I'll let you look there if you're curious in that. So let's find the standard deviation of this distribution. Right? So again, 50-50 here, right? So n is 20, p is 0.5, 1 minus p is also 0.5. And we knew from the previous question that n times p is 10. If I take 10 times 1 minus p, which would be 0.5, I get 5. So my standard deviation is just simply the square root of 5. And we could calculate that in our calculator. But you can see the mean and standard deviation are very easy to find in a binomial setting, which makes it even easier for us to apply the normal distribution. All right? Now, a couple of things before we jump into some example problems. First off, as we go through these examples, you're going to begin to ask yourself the question, why do we even need to know this? Because as we go through examples, we're going to do them both using a binomial distribution formula and a normal distribution formula. And you're going to see that the binomial distribution is a lot easier and a lot faster. So you might think, why are we even going to approximate it if I can just do this faster using a binomial distribution? But what we're trying to begin to establish in this chapter is that the normal distribution is an effective model of different types of distributions of data. And that's going to make our life a lot easier. You're right, the binomial distribution in and of itself is way easier than applying the normal distribution. But in future chapters and in future work in this class, the normal distribution will be the faster way to go. So we want to begin to establish this level of trust of applying the normal distribution, again, to model different types of distributions. So that's what we're looking at. All right, so here's our example. Let's say you're going to flip a coin 100 times. We want to find the probability that the results contain at least 40 heads. So let's do this on our calculator first, just using what we know about the binomial distribution from our first video. Okay? Well, again, we have that phrase at least 40 here. So hopefully you remember, anytime we see that phrase at least 40, we recognize that as the complement of the phrase at most. So that's the work that we're going to do again on our graphing calculator. So I'm going to do 1 minus the binomial CDF. My number of trials is 100. Probability of a success, which is getting ahead, is 0.5. And my K value in this problem, since we're doing the complement of at least 40, would be 39. So we can type this into a graphing calculator, just like we did in the first video. So into my distribution menu here. Let me exit out here. Let's do 1 minus first. 1 minus into my distribution menu. Scroll down to the binomial CDF. We'll go 100, comma 0.5, comma 39, and hit enter. And we come up with approximately 0.9823. So let's just jot that number down so that we can compare back to this here when we approximate with the normal distribution. Okay? So the first thing that we want to do here, before we approximate with the normal distribution, is we actually need to stop and think, is this actually appropriate for us to approximate? Is it appropriate for us to use the normal distribution? Because remember, we have this rule of thumb. So we need to take m times p and m times 1 minus p, and make sure that both of those are greater than or equal to 10. Right, well, in this problem, if we take 100, which is our n value, times 0.5, which is our p-value, we come up with 50, which is greater than or equal to 10. And if we apply the complement, 1 minus p, well, we know that's going to be the same thing, so both rules of thumb are met here. So according to this is going to be appropriate for us to use the normal distribution to approximate this binomial setting. So we're going to use a normal distribution, and our value should be close to 0.9823. So let's see if that holds true. Okay? Well, again, in order for us to use a normal distribution, we first need to find the mean and standard deviation. Well, if we flip a coin 100 times, right, we know that on average we would expect to get 50 heads. So we're going to be using a normal distribution where the mean is going to be centered on 50. So if I think about shading this, if I want to find the probability that there's at least 40, a 40 would be down here below 50, and we're ultimately going to be trying to find this shaded region right here. Okay? So again, in order for us to work with the normal distribution, we also need the standard deviation. So let's put our calculator up here, and let's calculate the standard deviation. So we're just going to simply take the square root of n times p times 1 minus p. So we end up with a standard deviation of 5. So let's slide this out of the way. Our standard deviation in this problem is 5. Well, now we're ready to set up the normal distribution. Again, at this point, you have two options. You can calculate the z-score and look that up on your gold packet, or you can use your graphing calculator. I'm going to use my graphing calculator just so you can see that work a lot easier. So we're going to set up the normal CDF on our graphing calculator. So if I slide this over here, we'll go to our distribution menu, normal CDF. When I look at my picture drawn here, my lower limit would be 40. My upper limit would be to infinity, since we're shaded off to the right. So 1E99. My mean is 50, and my standard deviation is 5. So I'm setting up the normal distribution using the characteristics of the binomial distribution in terms of its mean and standard deviation. So if I press enter, we come up with a probability of 0.9772, which you can see is pretty darn accurate in terms of what the binomial distribution found. And now again, I know this is faster to use to just work with the binomial distribution, but again, we want to establish a level of trust when it comes to using the normal distribution to model this. All right, so let's take a look at one more. Okay? Here's another example. So you're planning a survey of small businesses in your area, and you choose a simple random sample of 30 businesses. Experience shows that 3/4 of the businesses you contact will respond. So what is the probability that more than 20 will respond? So let's first just use our binomial distribution on our calculator to set this up. Okay? So let's think through this phrase, more than 20. Alright, so we know it's not a PDF since it's not exact, so we know we're going to have to use a CDF. Now, when it says more than 20, that means we would be looking at the numbers 21 and above. So we can think of that as saying at least 21. We know the complement of that is the phrase at most 20. So that's the work that we'll set up in our binomial distribution. So 1 minus the binomial CDF. Our number of trials is 30. That was the size of the random sample that we selected. The probability of success, which in this case is that they do respond, well, that's 3/4, so 0.75. And then our K value, again being the complement of what's being asked, would be 20 in this case. So now if we type that into our graphing calculator, we'll go into our distribution menu. Oops, let's go 1 minus first. So 1 minus, distribution menu, binomial CDF, so 30, comma, 0.75, comma, 20. Press enter. So there's our probability. We come out with a probability of 0.8034. Okay, so next let's approximate this with a normal distribution. Well, the first thing that we need to do is make sure that our rule of thumb is met. Now, when we check our rule of thumb in this problem, again, we're taking n times p. So if I take n, which is 30, times the probability of success, which is 0.75, well, that will come out to be 22.5, which is greater than or equal to 10. So we meet the rule of thumb for n times p. But remember, there's a second part to that. We also need to take n times the complement of the probability of success, which would be 0.25. And if we take n times 0.25, we only end up with 7.5, which is not greater than or equal to 10. So what that tells us is this will not actually be an accurate or a situation where it would be a wise idea to use the normal distribution in our approximation. Okay? And remember, our last problem met that rule of thumb. This time we don't. Okay? Now, if we were statisticians in real life, what option would we have here? I mean, if we need to meet the rule of thumb, what do we control in the setting? Well, we can't change the probability of success. Right? We don't have any control over that. But what we do have control over is the size of the selection. Right? We have a control over our number of trials. So in reality, if we wanted to use this data, we'd have to change the number of trials that we would use. And then we could apply the normal distribution. Well, let's go ahead and apply the normal distribution anyway, and I just want to show you how it's off a little bit more than what we saw in the last one. Okay? So, again, first thing we need is the mean and standard deviation. Well, we already have the mean actually calculated. That's the 22.5 that we used to check the rule of thumb. So if we think about this in the normal distribution setting, the mean is going to be in the middle, 22.5. We're going to find the probability that more than 20, so we'll shade above. Now we need the standard deviation. We can calculate that pretty easily on our graphing calculator. So again, I've got that right over here. So we'll take the square root of n times p, which is 22.5, times the probability of failure, basically, 0.25. For our standard deviation, the setting is 2.37. So let's go ahead and set up the normal distribution. We'll go to our distribution menu, choose the normal CDF. My lower limit, again, 20. My upper limit, 1E99. And my standard deviation, we just calculated that to be 2.37. And so we end up, I forgot to put my mean in there. Let's do that again. So lower limit, upper limit, mean is 22.5. And I know we're going to be off, but we're not going to be off by that much. So when I plug the mean in, we end up with a probability of 0.8542. So if we compare that to the probability that we found by the binomial distribution, we're a little bit over 5% off, all right, which we can see is not as accurate as the last problem. All right, so if we were to increase our number of trials, this probability value would come closer to what we actually found. All right. So again, just like the day before, I want to encourage you to complete the Google form below this video and be ready to participate in some class discussion over the next couple of days.